Hey Hire, so here's your starter. Do the pause the video, do the questions, and then unpause it. I'll go over the answers just now. So question 1A, what do we call the process of hardening an oil into a fat? It is hydrogenation. Okay, the addition of hydrogen. And what catalyst is used for this? Now this is one of the catalysts that you need to know. It is nickel. Yeah. Question 2A, name the process used to break down a fat into 3 sodium salts plus glycerol. Okay, so we're not breaking it down into 3 fatty acids, we're breaking it down into 3 sodium salts plus glycerol. So you would say alkaline hydrolysis. Now you can't remember what I said last lesson, you can't just say hydrolysis. You have to say alkaline hydrolysis, or you could have went for saponification. Okay, either one would be correct. What is a sodium salt? Again, this question comes up very often in past papers. What is meant by a sodium salt? It is a soap. Yeah, so easy, a soap. But a lot of people get that wrong. Yeah, a sodium salt is a soap. Now, see, what do we do to the 3 fatty acids when we create our soap, our sodium salt? Is we neutralise them. Yeah, we can use either sodium hydroxide to get a, in fact, it would be sodium hydroxide because the question says a sodium salt. So neutralise them with sodium hydroxide. Okay, remember fatty acids are acids, sodium hydroxide is a base, we neutralise it and we get a salt, a sodium salt, a soap. Okay, define the terms hydrophilic and hydrophobic. So hydrophilic is polar, yeah, and it means it is water soluble. Okay, it dissolves in water. Now, you couldn't just say, oh, it likes water. I know philic means to like, hydro means water. You can't just say it likes water. You need to say that it's water soluble. Okay, and hydrophobic, that would mean that it's non-polar and it would be fat oil soluble. Okay, and that's it. Right, question 3B, draw a soap molecule and label it using the terms hydrophilic and hydrophobic. So quite easy, soap molecule, remember, get your long chain in, and then you want to get your head, and obviously that there. Okay, so what we have, if I label this, remember that's a head, yeah, the Na plus isn't part of the head, okay, you've got a hydrogen bond between the minus and the plus. So this here is our polar head, and that would be hydrophilic. Okay, it's hydrophilic because it's water soluble, polar dissolves polar. And finally, this bit here, this is your non-polar tail, and of course that's hydrophobic. Yeah, it doesn't dissolve in water, it's non-polar, it dissolves in other non-polar substances. Okay, right, that's us, hope that was okay. So what we're going to do, our heading, literally soaps lesson 2. Okay, lesson 2. So what we're going to look at now, and I hinted at this last lesson, is we're going to look at the cleansing action of soaps. So basically, how do soaps clean? Okay, that's what we're going to look at here. So a wee background, and then I'll sort of give you like a textbook answer of how you should be answering these questions. So soaps are used to clean away dirt, grease, / oil stains, etc. Okay, now what's important about this and what you need to sort of get into your head is that the dirt, grease or oil are all non-polar substances. Okay, and you should already know that oil is non-polar. Yeah, because we spoke about that. It's got the long chain fatty acid attached to it. Okay, so yeah, dirt, grease and oil, they're all non-polar substances. So what I'm gonna do is I'm gonna give you a textbook answer to this, how you should construct your answer. And obviously diagrams, we love diagrams in chemistry. Yeah, helps so much. So I'm going to give it with diagrams. So a typical sort of past paper question would be, explain how this molecule could be used to clean dirt from a t-shirt or something like that, okay? And this is the sort of answer you would give. And I'll write in red pen for it, okay? So, first things first. You would start by saying, the non-polar, okay, so the non-polar hydrophobic tail, okay, and it's very important actually, I'm going to highlight this, it's very important that you say it's non-polar and you say it's the hydrophobic tail, okay? You need to let the marker know that you know that the tail part of the soap molecule is non-polar, and that means it's hydrophobic. Okay, so the non-polar hydrophobic tail of the soap molecule dissolves in the dirt / grease / oil. Now, it depends what the question's talking about. If the question's talking about dirt, you write dirt. If it's talking about grease, you write grease. If it's talking about oil, you write oil. Okay, so that sort of depends on what the question's asking. So, non-polar hydrophobic tail of the soap molecule dissolves in the dirt, grease, and oil, and the polar hydrophilic head dissolves in the polar water. Okay, and again, very important that you mention that you know that the head part of the soap molecule is polar and it's hydrophilic as well. Yeah, so non-polar hydrophilic tail of the soap molecule dissolves in the dirt, yeah, and, well, the non-polar dirt, and the polar hydrophilic head dissolves in the polar water. Okay, now I'm going to do a wee diagram here. Okay, so this bit, this here, is the dirt or the grease or the oil stain, whatever. Yeah, and what happens? Yeah, we know what a soap molecule looks like. I'll draw it up here. Soap molecule looks like that. Yeah, it's got the sort of negative head and blah blah blah. Now, what happens is the tail dissolves into the dirt and the head dissolves into the water. Yeah, so that's the dirt. The surrounding, the outside, is the water. Okay, and that happens like that. Now, I want to make a wee note here, because it's very important. SK are pretty strict with this, is that when you're drawing this diagram, yeah, even if you get asked to draw it, the tail has to be right in, okay? The head has to be flush to the duct. So make a wee note here. Tail has to be right in, okay? So not like this. If we just draw it again, you don't want to be drawing it like that, because that's wrong. Okay, the tail has to be right in, kind of like a nail. Yeah, if you hammer a nail into a bit of wood, it's the tail part that goes in, and the head is flush to the wood or the wall or whatever it is you're hammering into. Okay, so yeah, just make sure you know that. And obviously, like the sodium ions, they're going to be kicking about as well, but they're not really as important. Now what happens, this is the cool part. If we look at this, we've got negative heads, yeah? Have a wee think, what happens when we get two negatives that are in close contact with each other, yeah? Hopefully, you should know, is that they repel. Okay, two negatives repel, two positives repel. So what happens, the negative polar heads on agitation, yeah, and what I mean by, that's a key word as well, agitation. What I mean by agitation, like if you had a dirt stain, you're like agitating it, yeah, either with a bit of cloth or whatever, you're agitating it. So the negative polar heads on agitation repel each other, causing small droplets called micelles to form. Okay, that's just what we're calling a small droplet, a micelle. And again, quite a key word to get in there. Yeah, you want to be getting that word in there. Small droplet called a micelle, micelles to form. And what that looks like. Okay, obviously they repel each other, pulls apart the dirt, and we are getting droplets, little micelles that look like that. And what you've got here, yeah, remember, head, tail right in, the head flush to the droplet. What we're getting is this sort of structure. Yeah, and again, look at this. We've got two negative heads here. If they try to form again, because they're both negative, they're just going to repel each other. Okay, so that is your micelle. Now, yeah, draw the wee negative in. Those negatives are going to repel, so the droplets, the micelles, are going to stay like that. Okay, so our final bullet point is our negatively charged micelles repel each other and keeps the dirt / oil / grease suspended, yeah, suspended in the water where they can be washed away. Okay, and that's it. So again, this is just one of these answers that you really just need to memorise. You need to practice it. You need to write it out over and over again until you've got that pretty much memorised. Yeah. So the non-polar hydrophobic tail of the soap molecule dissolves in the non-polar dirt, grease, oil, and the polar hydrophilic head dissolves in the polar water. Do your diagram, show the marker that you know your stuff. The tail goes right in and the head is flush to the dirt. Okay, the negative polar heads on agitation. Okay, so we're agitating it, repel each other, causing small droplets called micelles to form. Okay, and that's what our micelles forming. And obviously you've got the soap molecules all around it. Yeah, this repels, the negatively charged micelles repel each other, and it keeps the dirt, oil, grease suspended in the water where we can easily just wash it away. Okay, that's why we use soap. That's why if you've got dirt or oil stain, you can't just use water. It doesn't work. Yeah, water polar, the oil non-polar, it's not going to wash it away. That's why we need soap. Okay. Right. Next part then. We are going to look at, I'll get my pen, my blue pen back. We're going to look at detergents. Okay. Now detergents work in pretty much, in fact, they work in identical ways to soaps. Okay, but there's just a slight difference. Yeah, and you need to obviously know that difference. So similar to soaps, but, okay, there's always a but tend to contain a sulfate group instead. Okay, so what we mean, like that there, is your carboxylate ion. Okay, so that's our soap. But our detergent, exactly the same. Yeah, it's got the long tail, hydrophobic tail. But this time, instead of the carboxylate ion, it's going to have a sulfate ion. Okay, so that's our detergent. And there is, of course, a reason as to why we have detergents, why we're changing that SO3. Okay, now detergents are used in places with hard water. Okay, and that's usually your sort of tap water containing calcium 2+ and magnesium 2+ ions. Okay, now we're quite lucky up in Scotland in that we have something called soft water where we don't have any of these ions, so we're able to drink water straight from the tap. But places like certainly the south of England and like France, Spain, they'll have hard water. I don't know if you've ever been abroad, but if you try and drink hard water, it's horrible. Okay, and that's the reason we can't drink it, is because it contains these calcium and magnesium ions. Okay, so why use detergents? Yeah, why would we not just, in cases of places of hard water, why do we not just use soaps? Why do we use detergents? So why use detergents? Soaps in the presence of hard water form a precipitate called a scum, and it's extremely unpleasant. Okay, extremely unpleasant. So this is why we need to use detergents, because if we use soaps and we're using hard water, they form a precipitate, a solid called a scum. Okay, and it's very horrible. So make a wee note here, detergents do not form a scum with hard water. Okay, and that's it. That's all you need to know about detergents, is that we use them in places of hard water because they don't form a scum. Yeah, the sulfate ion doesn't sort of react with the calcium, magnesium, and it doesn't form that horrible scum. Now, what we're going to look at now, yeah, and this will be the last thing that we look at, is emulsions. Emulsions. So we need to know what an emulsion is, and we need to know how emulsions work and what we need to add to emulsions in order for them. You'll see what I mean. So, an emulsion is a mixture of two or more immiscible liquids. Okay, you need to know what that term means. Immiscible. Okay, it's quite simple. An immiscible liquids are liquids that do not mix together. They do not dissolve in each other. Okay, a mixture of immiscible liquids. They do not dissolve in each other. Okay, for an example, water and oil. Okay, you can do this at home if you have some water and if you have some oil. If you mix it together, yeah, they start to mix, but then given time they just go back and they form two distinct layers. Okay, and I'll actually show you next live lesson. I'll show you exactly what happens there. However, what we're going to do, I'm just going to draw a couple of diagrams. Okay, so what would happen, we would pour water in and we would pour some oil on top, okay, and you're going to get two, because they're immiscible liquids, they don't mix, they're not soluble in each other, you're going to get two layers forming. Okay, now what we can do is we can mix, or a better word is we can agitate. Okay, we can agitate the mixture, we can shake it. Yeah, now what will happen is it will look like the water and oil are mixing. Yeah, so you've got wee sort of oil droplets here. But what will happen, yeah, if you just leave it, instead of mixing, they'll go back to the original two layers. Okay, so you've got the water and you've got the oil. It forms two layers again. Okay, it forms two layers again. So, emulsions. Why are we talking about emulsions? Because there are thousands of emulsions. Examples. Okay, milk is an emulsion. Paint. Paints are emulsions. My favourite, salad cream, is an emulsion. Shampoos. Yeah, many cosmetics. Ice cream. All examples of emulsions, yeah, etc. Because there are thousands of them. So they're all emulsions. So how come we don't see two or more distinct layers? Yeah, if you look at your shampoo, it's one mixture. Yeah, if you look at your salad cream, it's the one mixture. So if they're emulsions, why are they not forming two layers? If there's immiscible liquids within them, why are they not forming immiscible layers? And there's a reason for it, obviously. And that reason is it has something in it, okay? And that something that's in it is called an emulsifier, okay? So what we can do, chemists, because it is chemists, of course it is. Chemists do everything. So chemists can add an emulsifier. And emulsifiers are pretty cool, yeah? In that they make immiscible liquids miscible, yeah? They convert liquids that can't dissolve in each other, and that allows that to happen. So chemists can add an emulsifier, yeah? These help stabilize an emulsion, okay, by allowing immiscible liquids to mix. So we've got to think to ourselves, right, what is an emulsifier? What does an emulsifier look like? Why is that happening? Okay, so we head in how they work. Now this next part you need to know, yeah. So a lot of stuff you need to know, but you do need to know this. An emulsifier is a soap-like molecule. Okay, and that's important. It's soap-like. It's not a soap. We're not adding soap into salad cream. It's a soap-like molecule. So what that means, it consists of a hydrophobic sort of tail and a hydrophilic head. But it's not a soap. It's just like a soap. Okay, so an emulsifier is a soap-like molecule and is made by reacting. Now I'm going to put this in capitals because this comes up, usually multiple choice, but by reacting edible oils, okay, I'm highlighting that as well, you need to know that, okay, and is made by reacting edible oils and our favourite, glycerol, in a condensation reaction. Okay, this is where the whole fats, oil stuff starts to get complicated because we're bringing in emulsifiers now. Okay, so by reacting edible oils and glycerol, okay, I suppose we could highlight glycerol as well, in a condensation reaction. Okay, and we're doing that to form molecules with only, now again I'll highlight that, to form molecules with only one or two fatty acid groups linked to glycerol. And I'll give you an example of what I mean. Okay, so if we have a sort of long chain fatty acid, yeah, obviously it's a condensation reaction, we're making an ester link, and then that's attached to glycerol, and obviously that's attached to another ester link with a fatty acid chain, and that's attached to an OH, okay? So, very important that for an emulsifier, we only have one or two long chain fatty acids, yeah? Because if we have three, we've just made a fat and an oil, we've not made an emulsifier, okay? So we're after just two sort of long chain fatty acid groups linked to glycerol, okay? And if we do that, what we've now got if we highlight this hydroxyl group that's a part of glycerol, that there, because it's hydroxyl, it's got hydrogen bonding, that is water soluble. Okay? And that's your polar head. And if it's a polar head, that means it's hydrophilic. Yeah? It dissolves in water. Okay? Now, these two here, they, again, you should know, if I sort of highlight these two, they are oil soluble or fat soluble, whatever. They are your that is your non-polar tail, essentially. Okay, and that we should know a non-polar tail is hydrophobic. Yeah, and this is where the term soap-like molecule comes into it. Okay, it's definitely not a soap because it's not a salt. It's not a sodium or a potassium salt. But it's similar in that it's got a non-polar tail and it's got a polar head. Okay, it's got a hydrophobic section and it's got a hydrophilic section. So our equation here is we take an edible oil, we add it to glycerol, and we get an emulsifier. Okay, and remember, an emulsifier is 1 to 2 fatty acid chains linked to our glycerol. Yeah, propan 1, 2, 3 triol. So you do need to know that. You do need to know to make an emulsifier you take edible oil, glycerol. Yeah. Right, now, how they work? Okay, because obviously I've really just spoke about the structure of it, but let's start talking about how they actually work. Now, very similar to soaps, in that what we do is we've got our water and we've got our oil. Okay, and what happens, what we need to do is we need to shake. Like what we did in the last one, we shake the water and oil, yeah, and what that does, yeah, you should already know because we've spoke about it, what that does is that sort of gives us a wee droplets of oil. Okay, now once we've done that, once we've, again I'm saying shake, will be scientific, will agitate. So once we've agitated it, okay, this here, at this point, we add the emulsifier. Yeah, we're adding the emulsifier. Okay, and what that does, remember it's soap-like. Yeah, it's got a hydrophobic tail, it's got a hydrophilic head. So what happens is that I've kind of ran it as well, I'm only going to do 2, but what happens is the droplets, we're going to get the head and we're going to get the tails going inside. Okay, very much like what we do with a soap. Yeah, but this time it's not a soap, it's just got a hydrophobic tail and a hydrophilic head. And again, because you've got the wee sort of the heads, they are going to repel. Okay, so I'll make a wee note here. Polar heads of the emulsifiers repel each other and stay mixed. Okay, so every time they try and go back to the 2 immiscible layers, the heads repel each other, and that stops it from showing those 2 distinct layers. Okay, so they stay mixed given the appearance of one layer. Okay, and that's it. Now, if we look, say, tomato ketchup, that's another emulsion. Okay, usually you don't see two distinct layers, but usually what you need to do with tomato ketchup is you need to give it a wee shake first, and that is just to sort of split it again, okay, just to mix it fully. Now, obviously, something like tomato ketchup does have a shelf date. If we leave it by that, what happens, the emulsifier starts to break down, and then the minute it breaks down, it goes into all the immiscible layers, and that essentially ruins the emulsion, okay. But yeah, that's it. You need to know that an emulsifier is made up of edible oil and glycerol, and you need to know that emulsifiers are added to emulsions in order to make their two immiscible liquids miscible, essentially. Okay? Now, again, we spoke all about that, so it's a big lesson. Yeah, we have done quite a lot today. So you need to take time to go over it, make your notes, practice your answers. Okay, you need to know about the soaps. The whole non-polar hydrophobic tail dissolves into the non-polar dirt, grease and oil, and then obviously the polar hydrophilic head dissolves into the water. Okay, you need to know all that stuff. You need to know about the agitation, how it repels and it forms the micelles. Okay, and how the negatively charged micelles repel each other, and that way we can just wash away the dirt. Yeah. Know that a detergent contains usually the sulfate ion, and that we use detergents in places with hard water, okay, so that they don't form a scum. Because if we just use a soap, we get a scum, but if we use a detergent, we don't. Okay, and then obviously the last thing, I'm not going to go over it again, but the last thing, you need to know what an emulsion is, and you need to know why we add an emulsifier into an emulsion, and so on, and the process, the chemistry behind that. Yeah, an emulsifier, it's an edible oil reacted with a glycerol, yeah, to form a hydrophobic tail, yeah, one or two, and then a hydrophilic head. Okay, so I'm going to put up some working teams, and I will leave it there for today. Thank you.